Guys, welcome once more to our YouTube channel. So today we are looking at the engineering entrance examination into College of Technology, University of Buea, Physics 2022, Episode 1. Without much ado, let's dive right in. So guys, just before we dive in, at Knowledge Center, we just really want to promote science in the country. We want to encourage the studies of science in young learners, and we want to make sure that they are crazy excited and crazy enthusiastic about every possibility that the landscape of science offers for them. So you can check out our work on Twitter, on Facebook, on YouTube, and so many other social media platforms. Well, just check out the name Knowledge Center Cameroon and you'll find us right there. Let's go. All right, guys. So question one says units of the physical quantity can be expressed in terms of the fundamental or base unit of the international system. In which pair are the fundamental unit correctly matched to the physical quantity? Well, we're just going to go around, right, and then just make sure we pick each one of these pairs and see if they are correctly matched to their base unit. So the first there is charge. Charge is Q. Q is current times time, right? So base unit of Q will simply be the base unit of current multiplied by the base unit of time. So we have ampere second there. Clearly, it's not correctly matched, so A is off. B says power, so power is force times velocity, so we can just get the base units of power to be the base units of force, which is kilogram meters per second squared, multiplied by base units of velocity, which is meters per second. So when you multiply those two together, you have kilogram meters squared per second cube, right? So that guy right there is correctly matched. So power, and it has the same or the right base units. So right there, our answer is B. But we'll just go ahead and do C and D to make sure that they are wrong. So C says potential difference. Well, power is IV, so our potential difference is basically power over I. So we get the base units of V to be the base units of power divided by the base units of current. Now, power is already kilogram meter squared per second cube here, so divided by current, just ampere. So we have kilogram meter squared per second cube per ampere. Clearly, that's not what we have here, right? So we have per second cube, but this guy does not have it. So D says energy. So energy is just basically work done, right? Force times distance, and so we have base units of energy to be kilogram meters squared per second cube, right? Because okay, no, I've made a mistake here. So it's actually kilogram meter squared per second squared. Sorry about this. Really sorry about this because force is kilogram meters per second squared, and then distance is just meter. So this is per second squared. Anyways, D is also wrong. So our answer is B right there. 2. A car accelerates uniformly from rest along a straight road. Which graph shows the variation of displacement x of the car with time? All right, so we're just going to use one of Newton's equations of motion here, s equals ut plus half at squared. And so since the car is accelerating from rest, you have u to be 0, and so s is half at squared. But notice that s is x, right? The displacement of the car is x. So we're just going to replace s with x. And so we have a over 2 here, t squared. So this is an equation. Clearly, this is a quadratic equation in terms of t, right? So the key here is recognizing that this is a quadratic equation whose value of a is greater than 0. So the value of a here is greater than 0. That means that the quadratic equation is going to have a minimum turning point. So a and c are already off because a is a straight line, c has a maximum turning point. So these two guys are off. So b or d, b can have a minimum turning point, d can go down and then have a minimum turning point and then turn back up. So either b or d are right. Now, but the thing is, there's no value for b and there's no value for c in this particular quadratic equation. Can you notice that? So you just have c squared term there. There's no t term and there's no constant term. So what that means is the turning point is actually going to lie on the y-axis. So boom, our B is our answer. So yeah, answer is B. We move on to the next. Which of the following statements is correct? The first action on an object is equivalent to, okay, so F is basically ma, right, from Newton's second law. So but A is a time rate of change of velocity. So you realize that this change in velocity multiplied by mass here is our impulse, right, or change in momentum, right? So you realize that our answer is already B because B says the impulse it receives per second. So change in momentum per second, that's in impulse per second. So that's our force, right? Good. A gas molecule of mass m in a container moves with velocity v. If it makes an elastic collision at right angles to the walls of the container, what is the change in momentum of the molecule? All right, this is very easy. So you're moving towards the wall. So this is the direction of motion, this v here, and then you hit and then you bounce off with the same velocity v. Okay, so because the collision is of course elastic, right? So coefficient of restitution there is 1, right? So boom, the particle just reverses direction but maintains its velocity or its speed. So we have change in momentum to be mass times change in velocity. So you realize that, well, v minus u, but again, v and u are in opposite directions. So that's why I'm indicating negative u here, right? Because velocity is a vector quantity. So when the directions are opposite like this, you want to make sure that you include that in the calculation. But v and u are equal, so u is also v. So this negative negative, we have positive there, so we have v plus v, that gives us 2v. So our change in momentum is just basically 2mv. So our answer there is D. The graph shows the variation with time t of the force F acting on a body. What physical quantity does the area represent? Okay, so this area X is actually area under the graph, and that's very easy to get from calculus, basically integrating what is on the y-axis with respect to what is on the t on the x-axis. So you have integral of f delta t there, that gives you the significance of the area under the graph, which is basically what f times t, really. That's why I'm saying the sum of small changes in f multiplied by the small changes in t. So x represents the physical quantity identical to ft, which is impulse, right? Which is equal to change in momentum. So change in momentum is equal to impulse, which is equal to force times time. Okay. So which is identical to change in momentum, which is equal to impulse. So our answer there is just the change in momentum of the body. Any one of these ones, if they said if the alternative would have read impulse, then that would have also been the answer. A lunar landing module is descending to the moon's surface at a steady velocity of 10 meters per second at a height of 120 meters. A small object falls from its landing gear. Assuming that the moon's gravitational acceleration is this, at what speed in meters per second does the object strike the moon? Okay, this is a very interesting question. It's in Nekon and Parker. So for those of you who solve Nekon and Parker, yeah, this question is one of the mechanics questions in Nekon and Parker. MCQ too. So if we solve it here and you really want to check it again, you can go and solve it in Ekman back and then check the answer behind it will correspond to what we are going to have here. So the initial velocity here is 10 meters per second. That is the key. The key is recognizing that if something falls off from an object that is descending towards the moon at a particular speed, that thing falls off at that same speed. Okay, it's like, okay, okay, we're in an aircraft. The aircraft is moving due east at maybe 100 meters per second. If I drop a coin off that aircraft, that coin is actually going to have an initial horizontal velocity of 100 meters per second, because I'm in that initial frame of reference. I share the speed of that reference frame, and so every other object in that reference frame is in motion at 100 meters per second, 100 meters per second. Okay, so you realize that, all right, so this thing is falling off, its initial velocity is 10 meters per second. That's just the key here. You don't recognize this, you think that it's going to drop off and then drop off with an initial velocity of 0. That's where you're going to feel the problem. So the height there is h. Our a is 1.6 meters per second squared. So we're going to use our simple equation of motion, v squared plus u squared plus 2as. So our v is that. So just key in what we know, and our v is 22 meters per second. So our answer there is A. A ball X is projected horizontally from a certain point, and a ball Y of the same diameter but twice the mass is released from rest and allowed to fall vertically from the same level. Air resistance negligible. Which one of the following will occur? Well, the fact that air resistance is negligible, I really don't care about their volumes. You get. Well, I'm sure this is talking about the time. So A will hit the floor just before X. All of that will be talking about time. Which one hits the floor first? Which one hits the floor later on? Okay, all of that. So this is just a tiny table, X, Y. So they have the same volumes but different masses. Now, but the time for them to hit the ground, which is basically time of flight, is basically 2h on g. If they are released from the same height, so one is dropped, one is shot at the horizontal velocity, the truth is you just want them to have the same height. So because they come from the same height, so from a certain point, right? Good. So if they come from that same point, then we are good, because their time of flight will be the same, and our answer will just be C. A 1.0 kilo ohm resistor is thermally insulated and a potential difference of 6 volts is applied to it for 20 minutes. The thermal capacity of the floor resistor is this. The rise in temperature in Kelvin is, well, here you just want to make sure that electrical energy supplied will be equal to heat generated by the floor resistor, right? So IBT, which is the electrical energy supplied, is basically MC delta theta. And so we can switch some things. M times C, this small c here is specific capacity, but notice that you have heat capacity instead. So how do I get heat capacity from specific capacity? Well, heat capacity is just basically specific capacity multiplied by the mass of the object. So MC gives me big C. Okay, so that's just what I've done there. And then I don't have I, so I've replaced I with what? V over R according to Ohm's law. So V over R multiplied with this V, I have V squared over R. So delta theta now makes that, so I just make delta theta the subject, and so that's what I have. Key in what my V is. V is 6, square that, my time is 20 minutes, I convert that to seconds. My C here is the heat capacity, which is 9, and then my R is 1 kilo ohm. So I have delta theta as 4.8. Well, the key here is I don't really know if this resistor or the resistance here is actually 10 kilo ohm or 1 kilo ohm. If it's 10 kilo ohm, then the answer is C. If it's 1 kilo ohm, then there's no answer. So I'm just saying that the answer is C because, well, this is 4.8 and this is 0.48, so it makes sense that this guy should have been 10 kilo ohm. All right, but you get what you're supposed to do there. Let's move on. The fixed mass of an ideal gas initially has a volume V and absolute temperature T. Its initial pressure could be doubled by changing its volume and temperature too. Well, this is very easy. Ideal gas equation is PV equals nRT. So PV over T becomes a constant because, hey, remember that this is a fixed mass of gas. So if it's a fixed mass, it means that the number of moles in that gas is a constant. And then you have the universal gas constant R, which is also a constant. So PV over T would be equals to constant, which means that P1 V1 over T1 equals to P2 V2 over T2. Why? Because PV over T is a constant. So now you want to get P2, right? But you want to make sure that, listen to what it says, its initial pressure could be doubled by changing it. So you want to double the initial pressure. So you just want this P2 to be 2 times P1. So you want V1 over V2 multiplied by T2 over T1 to give you 2. So you just have to go through all of these things and then see which one gives you 2. But it's easy there to just recognize that P would give you that. Because if I take V over 4, uh, so the volume now changes to V over 4. So I'll have V over V over 4. That gives me 4 here. So this ratio will give me 4. And then here I would have uh, T over T over 2. No, T over 2 because this is T2. T over 2 over T. So that will give me half. Half times 4 would give me 2. So that would mean that the pressure has doubled. You get the trick. Yeah, so you just have to really make sure that you can put this and then see which option will give you this result here to be 2. And that's B. All right, let's move on. A fixed mass of gas occupies a volume V. The temperature of the gas increases so that root mean square speed of the gas molecule is doubled. What would the new volume be if the pressure remains constant? All right, so root mean square speed, of course, is square root of 3 times pressure divided by density. So I'm just going to call C1 for the first root mean square speed. So in place of density here, remember that density is mass over volume, right? So mass over volume here, so the volume can go up. So I have 3 times P times volume divided by the mass of the gas. So I'm going to call that equation 1. So my equation 2 now would be V2 here. So this V here is just for the first case, and then now we have V2 here. So if I ratio C2 to C1, remember that you want the root mean square speed to double, right? So C2 over C1 should give me 2. So if I ratio that, these 3, right? So I'm just ratioing equation 2 to equation 1. So if I ratio, I'll have 3PV2 over M, right? Multiplying M over 3PV. So you're just ratioing this. Yes, just ratio it. That's what I'm just doing. So this 3PV or this 3P goes over this 3P. This M goes over this M. So I'm basically left with what? Square root of V2 over V equals 2. So I can square both sides, and so my V2 will just be what? 4V, right? Good. So you want the volume to do what? To quadruple, so that the root mean square speed doubles. There you go. D. Okay, you go ahead and read the questions about coplanar forces. Well, so we're just saying that the result of coplanar forces is F1, F2 plus F3 plus da 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 da. But then if the forces are acting in the same direction, then you simply have this addition. If one is acting the opposite direction, maybe F2 is acting the opposite direction, you have F1 minus F2 then plus F3 plus da, 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 right? Good. So what we're saying is, how do I then get the maximum possible resultant of coplanar forces? Well, the maximum possible resultant is only going to occur when all the coplanar forces have the same direction. So you get 5 plus 4 plus 3. That gives you 12. So this is the maximum possible resultant force you can create from these coplanar forces. So this 16 here is already off. It's not possible to ever get 16 from these coplanar forces as a resultant. So, but let's talk about how you can get this 4 and how you can get this 0. Now, this 4 here, like we said, now, if 4 Newton is a force that's acting opposite to 5 and 3, then we'll get 5 plus 3, which gives us 8, minus 4, which gives us 4 Newton, telling you that, yes, B being 4 Newton is possible to be a resultant of these coplanar forces if the 4 Newton is acting in opposite direction to 5 and 3. Now, how do I get 0? Now, I just want you to look at this. These are Pythagorean triplets, 3, 4, 5. They are Pythagorean triplets. So if I get over here and I draw a right angle triangle, so first you have this 4 and then you have this 3, and then you have the hypotenuse will be 5, which will be just this resultant right here. So the resultant of these two forces here would be 5. So if I get a third force to act opposite to the resultant of these two forces, which is 5 Newton here, you realize that the resultant of the forces in this system, which what system? The system of 4, 3, 5, 4 Newton forces would basically just be 0 because the resultant of these 3 and 4, which are the base and height of a right angle triangle, would just be 5. And then if this 5 is acting in opposite direction to this guy, then I basically have the resultant to be 0 right there. So this would be concurrent coplanar forces in this particular case. So you can get 0 there as a resultant. So 16 is the guy off, and our answer there is B. A particle moves in a circular path at constant speed. Which one of the following statements is correct? Well, the answer is just clearly C, right? Because there is no change in the kinetic energy of the particle. Why? Because it moves at constant speed. Like, it's very easy. But let's see why A, B, and D are wrong. A says the velocity of the particle is directed towards the center of the circle. That's not true. It's directed tangential, right, to the circle, right? At every single point where the particle is. So the acceleration is what is directed towards the center, not the velocity. There is no force acting on the particle. That's not true. Centripetal force acts on the particle. Of course, you know that. And then there's tension too, acts on the particle. And sometimes that tension can provide the centripetal force. D says the particle has an acceleration directed along a tangent to the circle. That's not true. The acceleration is directed towards the center. So our answer there is pretty much C. A ball of mass m, which is fixed to the end of a light string of length L, is released from rest at x. It swings in a circular path passing through the lowest point y at speed v. If the tension in the string at y is T, which one of the following equations represents a correct application of Newton's laws of motion to the ball at y? So at y, it has a speed v. So it's very easy, right? So the answer is just C there. Well, let me just show you why the answer is C. So you have summation F equals MA at this particular point y. So at x, I've just indicated at x. So at x, the tension is just what is providing the centripetal force, which is mv squared over r, right? Because, I mean, you want the force that is pointing towards the center will just be the tensional force in the string. But certainly it's going to be different from this v here. Oh, I should have indicated that this v is different because the speed at x is different from the speed at y. Of course, I hope you know that. So at y, t minus mg equals mv squared over r. So what do we know? Why do we say this? Well, because at y here, the weight of the particle is acting downwards, the tension is acting upwards. So the resultant of those two opposing forces acting on the particle gives you the centripetal force towards the center. So you have tension is acting towards the center, so you have that tension first, minus the force that is acting away from the center, which is mg, should give you that centripetal force. So that's it. The time period of a pendulum on Earth is 1 second. What would be the period of a pendulum of the same length on a planet with half the density but twice the radius of Earth? Okay, so let's work that out. So time period is 2 pi L over G for a pendulum. On Earth, you have 2 pi L over G on Earth. So this is gravitational field intensity at the surface of the Earth. T on the surface of the moon would be 2 pi square root of L over G at the surface of the moon. Okay, so let's just do some little math here. So we ratio the time period on the moon to the time period on Earth. So we're going to get this. So just really ratio these two things, right? 2 pi go to 2 pi, and then you have these square root things applying like that. Okay, so we're going to now have GE over G because this L goes off. So we're going to have square root of GE over GM. But then I want you to notice that GE there is basically universal gravitational constant multiplied by density of the Earth multiplied by the radius of the Earth. And then G of the planet, which I'm calling M, would basically be universal gravitational constant multiplied by density of the planet multiplied by radius of the planet. So I'm just giving you highlight here, or like a hint where this is coming from. So G is Gm over R squared, right? So if I multiply up and down by the radius of the planet, I'm going to get my G to be Gm R over R cube. But then this R cube, remember, that gives me volume. And then I'm going to have mass of the planet divided by its volume, which gives me the density of the planet. So you realize I'm simply left with G rho R. So that's how gravitational field intensity is basically universal gravitational constant multiplied by density of the planet multiplied by the radius of the planet. So this is where this is coming from. That's why I'm replacing GE with density rho R. That makes sense? Okay, hopefully it does. So if you put in everything, so it says here that what will be the okay, so with half the density but twice the radius. So half the density means that PE over PM would give me 2, but half the radius. Half the radius means that RE over RM will give me half instead. So 2 times half will give me back 1. And so I'm basically just left at the same spot. So I'm left with T square root of 1 because this G goes over this G. And so I'm left with Tm equals to Te, right? So the period does not change. And so our answer there is just B. 1 second on Earth, 1 second on the planet. There we go, guys. Thank you so much for watching the video to the end. If you liked it, please subscribe to our channel, ring the bell, share the content. Thank you so much. We love you. Keep preparing so well for your exam. All the best.